In this final video segment, we're taking a look at Section 3, problem number 4. And here we have two different types of workers in a given labor market. One is low skilled, receiving a relatively low wage, which we would expect, and one is more highly skilled, receiving a relatively high wage. And we're going to call them workers high and worker low. The minimum wage in this market is $7.25, and L is equal to the number of workers in hundreds. So low has the labor demand schedule parameterized by labor demand for low is equal to 20 minus 2 times W of low. And high labor demand is going to be labor demand for high is equal to 20 minus the wage for high. And I've said that the labor supply in this market for both types of workers is going to be the same. So here we then have where I ask you to identify the own wage elasticity for workers at each firm based on a proposed wage increase of 10%. Well, how do we know where they start out with their wage? Well, to find that out, we have to think about this labor supply and labor demand. So we've got labor demand, labor supply, equate them to one another. We can then find the W star for low, that's 7.67. It's above minimum wage, of course. And that's also our initial level. If that's our starting point, that's W1. And then L star is 4.67, and that's L1. And we can do the same thing for high, where we should have seen W star for high at 11.5, which is W1 for high, and then L star for high at 8.5, which is L1 for high. Then we have to think about what is W2 and L2 for each of these types of workers to motivate an elasticity. Well, to do that, we know that there's a 10% increase in wage, so W2 is going to be W1 times 1.1, or for low, it's 8.44. And then to identify L2, or the number of workers that would be employed at that wage, we're simply going to take that 8.44 W and substitute it into the labor demand equation for low, and we find that the number of workers, or L2, becomes 3.12. So W1 and L1 are 7.67 and 4.67. W2 and L2 are 8.44 and 3.12. We've done the exact same thing for high, and we've learned for high that W2 is 12.65, L2 is 7.35. And then we simply set up the equation for demand elasticity. Only in this equation, we really haven't bothered calculating the denominator because we're told something about the denominator. So we know that the denominator is the change in wage, the numerator is a change in L. We're told the change in wage is 10%, so we're just using 0.10 as 10%. We know that. But we do have to identify the value of the numerator, and that's going to be L2 minus L1 divided by L1, which is going to end up giving us a negative value such that we have a negative elasticity of negative 3.31 for low. And for high, we do the exact same thing. We end up with a negative elasticity, which we would expect because these are demand elasticities, own wage demand elasticities, of negative 1.35. Which frankly is also elastic, just as low at negative 3.31 is elastic, but it's less elastic, which doesn't surprise us. And it doesn't surprise us that it's still elastic because if you think about it, a wage of 8.44 or 7.67, that is low enough wage to certainly be low skilled, and we know low skilled workers are elastic, which is shown by the elasticity here. But if we're thinking about 11.5 and 12.65 wages, well, that's higher. So on a relative basis, it's higher. It's on a relative basis going to be a higher skill set. So we would expect it to be on a relative basis a lesser or lower level of elasticity, which negative 1.35 is. It's not as elastic, but it's still elastic. It's just not as elastic. So it's elastic, but less so. In B, I said, okay, what do you expect to happen to the total wage bill for a firm employing these two types of workers in the event of a wage increase? Well, remember the basic rules. When a worker has an elastic labor demand, when the wage rises, the total cost of labor goes down. That's the total wage bill. when they're inelastic, so a elasticity that is less than the absolute value of -1, when a wage rises, the total cost of labor or the wage bill rises. So we would expect, since both of these are elastic, to find that as the wage rises, the total wage bill will go down, consistent with the first rule. And in fact, when we test this, we can say, okay, W1 times L1 gives us a wage bill to begin with, and then W2 times L2 gives us the new wage bill, and we see that it's gone from 35.82 to 26.33. So as the wage rose, the total wage bill went down. We have the exact same thing happening over here for high. We see that it starts at 97.75 and then moves to 92.98. So once again, it's gone down. But maybe important to point out the dynamics of that downward movement. Here, this one went down by a relatively large percentage. That's going to be something like a third or almost a third, more than a quarter. Whereas here, it went down by 7 or 8%. Well, that's because this one high is less elastic. It's more inelastic, and so it's going to be coming towards this point to reach the basic inelastic rule concept. So then I asked, suppose the wage increase for low result in a cross wage elasticity. Remember, a cross wage elasticity is a percent change in L for worker I divided by the percent change in W for worker J. So a different worker, and I'm saying if that equaled some negative value, then what do we know? Well, a cross wage elasticity that is negative tells me that we have a complement here, so rather than a substitute. And so let's think about this. So if we have two workers, they're complements to one another. Let's say a plumber and a framer on a residential construction site. If the wage of a plumber goes up, then the cost of construction is higher. If the cost of construction is higher, the cost of the home is higher. Fewer homes will be purchased when the prices go up, so we need fewer carpenters. So if the wage went up for plumbers, the number of carpenters needed goes down. We have a negative value. That's because they're complements. Had they been substitutes for each other, it would have been just the opposite. It would have been positive. So we know those things, and so I was looking for some articulation of that. Some of you pegged this very nicely. Some of you struggled with this, that tackled this question. And then finally, say, do the elasticity values and types we calculated for each worker in Part A change if you use the midpoint formula? So the only real difference we're dealing with here is we're motivating the midpoint formula, slightly more complex than the simple formula we used initially. And in the initial question back here, if you use the midpoint formula here, I was okay with that, but I asked you to use the simple formula. So I didn't discount you much if you use the midpoint formula, because frankly, if you understand midpoint, you almost certainly understand a simple, but I was looking for a simple elasticity. So here, we're simply going to motivate this equation where we have L2 minus L1 divided by L2 plus L1 divided by 2. That's our numerator. And then W2 minus W1 divided by W2 plus W1 divided by 2 for our denominator. And we're simply going to motivate that for each of the values that we have. And we're going to find that high has a negative elasticity of negative 1.52, which is a little bit more elastic than we saw when we just used a simple formula. Recall that the midpoint formula is more accurate, especially when there's a large change. When the change in wage is very small, then the differences between simple and midpoint will be insignificant if measurable within a 2 decimal point rounding. So here we find that it's a little bit different, but not much. And so here for low, we go through the same exercise, and we find that we have, still elastic at negative 4.16, which is yet more elastic. Doesn't surprise us. The other one was more elastic up here as well, although just minimally so. But this one is meaningfully more elastic because these workers at a low wage are meaningfully more elastic.